Wow, you guys have sent us a ton of stuff about graph algorithms.
Yeah, looks like someone's been digging deep into data structures and computer science.
Definitely looks like it. So, what do we actually mean when we say graph in computer science? Like,
hmm
it's probably not the kind of graph I used back in, high school math class, right?
Nope. Not bar charts or line graphs or anything like that. In computer science, a graph, well, think of it as a way to show relationships, like a structure
Yeah.
made up of these things called nodes.
Okay.
And they're connected by, we call them edges. Think of like a social network. People are the nodes and their friendships are the edges. Or like a map, cities are the nodes and the roads connecting them, those are the edges.
Oh, that makes a lot of sense. So then how do we actually build these graphs? Your notes mentioned a adjacency list. What's that about?
Ah, adjacency list. That's one of the most common ways to represent a graph when you're actually writing code.
Hmm.
It's basically like a dictionary. Each key is a node, and the value is a list of all the nodes it's connected to. Easy way to keep track of all the relationships.
And I see some Python code here using collections.defaultDict. Is
Uh,
that like a special dictionary just for graphs?
Default dict is super useful for this. It automatically creates a new entry, like if you try to add an edge to a node that isn't in the dictionary yet, so you don't have to like write extra code to check if the node already exists. Makes things a lot simpler.
Gotcha. So we've got our graph built. How do we explore it, I guess? I see traversing the graph in your notes. Not really sure what that means.
Think of it like exploring a maze. You've got two main ways to do it. Breadth first search, which we call BFS,
Oh,
and depth first search, or DFS. So in BFS, you explore all the paths that are a certain distance away before you move further out,
okay.
kind of like checking all the rooms connected to the entrance of a maze before going deeper.
Okay.
DFS, though, that's like picking one path and just following it as far as you can go before you have to backtrack.
Oh, okay. So two different approaches. What are some of the things we got to think about when we are choosing which one to use?
Well, one big thing is how long it takes, the time complexity, how many nodes and edges are in the graph. In the worst case, like where every node is connected to every other node,
Yeah.
it can take time proportional to the square of the number of nodes. Gets real slow for big graphs.
So bigger graphs, more time to traverse. Okay, that makes sense. Something I've never quite understood. How do trees relate to graphs? I know they're both important, but...
A tree is actually a special kind of graph.
Uh-huh.
Think of a family tree, right? You've got a hierarchy, starts with a root node, and there's no cycles, meaning you can't loop back.
Okay.
Basically, all trees are graphs, but not all graphs are trees.
So trees are graphs, just with some extra rules.
Hmm.
No cycles allowed. Makes sense. You know what? Let's move on to something more practical. I see validating tree structures in the notes. What's that all about?
So say you have some data and it's supposed to represent a tree, but you need to check if it actually follows the rules. That's validating the structure.
Hmm.
A valid tree needs to be connected. There has to be a path between any two nodes
Okay.
and a cyclic, no loops.
Got it. So we have to make sure there's a way to get from any node to any other node, but without, going in circles. Sounds like a job for our traversal algorithms, maybe.
Exactly. We can use BFS to check both conditions. It helps us see if all nodes are connected and make sure the number of edges is correct so there aren't any cycles.
Wow. BFS does more than just mazes, huh? Make sure our data is structured right. That's pretty cool.
Yeah, it is. Shows how versatile they are. Now, this whole thing about exploring paths reminds me of the word ladder problem.
Oh, yeah, word ladder. Try to connect two words, change one letter at a time.
Yeah.
I love that game. How do graphs help us solve that?
Well, think of the word ladder as a kind of hidden graph.
Okay.
If words are the nodes, and they're connected by an edge if they only differ by one letter.
Right.
So solving the word ladder, we're actually finding the shortest path between two words in this hidden graph.
That's a neat way to visualize it. Which traversal algorithm helps us find the shortest word ladder?
BFS is perfect for this. It goes layer by layer, so it's guaranteed to find the shortest path.
Oh, so BFS for efficiency. I'm really starting to see how useful these algorithms can be.
And there's even some clever coding tricks, like using sets to check for those neighboring words makes things run faster.
Sets, like in math. Never would have thought they'd be useful here.
Yeah, you'd be surprised. Little details like that can make a big difference.
Makes sense. Now on to something that sounds a bit more sci-fi, cloning a graph. Is this as complicated as it sounds?
Well, it's about making a deep copy, not just copying the nodes, but recreating all the connections between them.
Right, so a real duplicate, not just a copy-paste.
Exactly. So we use BFS again, traverse the original graph, systematically create copies of each node and the connections.
Wow, BFS is a real workhorse.
Yeah. It is. And we use a dictionary to keep track of which original node goes with which copied node to make sure all the relationships are right.
So BFS helps us create an identical twin graph. That's pretty amazing. We've covered a lot, building, traversing, even cloning graphs. What else is there?
Lots more to come. Your notes talk about finding all paths in it's called a directed acyclic graph.
Okay.
And then deciphering alien languages, even reconstructing flight itineraries.
Alien languages. It's got to wait. Give me a break first. Be back in a flash. All right, we're back, ready to tackle some more of these graph ideas. You mentioned directed acyclic graphs before. What are those exactly?
Directed acyclic graph, or DAGI, basically a graph where the edges, they have a direction. Like one-way streets, acyclic means there's no loops. You can't go back to a node you've already visited. You see these in like project plans where tasks have dependencies, or even just showing how information flows in a complex system.
So like a slow chart, only moving forward. Gotcha. What kind of problems do we solve with DAGs then?
Your notes talk about finding all the paths from a start node to an end node within a DAG. Like imagine a project plan. Each node is a task. Edges show the order things need to be done. Finding all paths in that DAG, it show you all the different sequences of tasks to reach the final goal.
Okay, so finding all the ways to get from A to Z in a project, that's the problem. How do we do that with code?
Depth first search, DFS, remember, it's like that maze exploration, going as far down one path as possible before backtracking.
Right.
In a DAG, DFS explores all the paths systematically, keeps track of each one until it hits the destination.
So it's like trying every route in our flowchart, noting all the ones that lead to the goal. Pretty thorough.
It is, and we can store those paths in a list as we find them. Now, shifting gears a bit, let's talk alien languages. Sounds crazy, but graph theory helps us there too.
Wait, what? Alien languages? I gotta hear this.
Imagine we get a list of words from an alien dictionary, but we don't know the order of their letters. We can make each letter a node.
Okay.
And if letter A comes before B in their alphabet, we draw an edge from A to B. Do this for all the words. We build a graph of their alphabet order.
So we're mapping their alphabet with a graph. But how do we actually figure out the order of the letters from that?
That's where topological sorting comes in. It finds a linear order of the nodes following the direction of the edges.
Okay.
So apply that to our alien language graph. Boom, we get a possible order for their alphabet.
Topological sorting. Putting the letters in order to make their words make sense. That's wild.
Pretty neat, huh? And like other graphs, gotta make sure there's no cycles, otherwise their alphabet contradicts itself. Wouldn't make sense.
Right. Cycles mess things up. Okay. From aliens to something a bit more down-to-earth, reconstructing flight itineraries. Graphs can plan trips now.
Oh, yeah. Say you've got a bunch of flight tickets, each one with a departure and arrival city. You got to figure out the whole trip, starting from some airport, using each ticket only once.
Okay, got it.
Airports are the nodes. Each ticket is an edge going from departure to arrival city. We've got a graph.
So we got to find a path that uses each edge once
Yeah.
and only once. What do we call that kind of path?
Eulerian path. DFS comes in handy here, too. The code in your notes, it uses DFS to explore, keep track of the itinerary,
Okay.
uses a priority queue to make sure the itinerary is in alphabetical order, nice and neat.
DFS, saving the day again, keeping our travels organized. These algorithms are amazing, seriously.
They are versatile, that's for sure. Okay, last one, counting connected components in an undirected graph. Imagine a social network, people are nodes, edges are friendships.
Right.
A connected component, it's like a group where everyone's connected, directly or indirectly.
So identifying the different friend groups within a bigger network, what's the point of counting them?
Tells us about the network structure, lots of small groups, or one giant web. This info is useful for, like, understanding social dynamics, analyzing communications, even designing transportation systems.
So connected components give us the big picture. How do we count them, though? Seems complicated, especially for a big network.
Yeah, doing it manually would be a mess. But we've got this data structure called Union Find. Keeps track of connected components really well.
Union Find, okay. How's it work?
Think of it like clubs. Everyone starts in their own club.
Okay.
When we find edges connecting folks from different clubs, we merge them together.
Right.
The number of clubs we end up with, that's the number of connected components.
So start separate, merge as we find connections. Simple but smart.
Exactly. And we've got efficient algorithms for union finds, so we can handle those big, complex networks.
We've covered a lot today. Started with the basics, explored traversal, then dove into these really cool applications.
It's pretty amazing what you can do with graphs. but we've only just scratched the surface. There's so much more out there.
Well, I'm feeling a lot more graph savvy now. But before we wrap up, I gotta ask, what's the most mind-blowing graph application you've seen?
Ooh, that's a tough one. But one of the most fascinating areas is AI, especially deep learning,
Oh.
neural networks, things revolutionizing image recognition, language processing. They're essentially graphs at their core.
So those AI systems that can translate, compose music, even diagnose diseases, they're all powered by graphs. That's incredible.
It is. The neurons are the nodes, and the connections between them, with their weights, are the edges. Graphs are kind of the foundation for so much of our tech.
Wow, graphs are everywhere. As our world gets more connected, understanding them is going to be more and more important.
Definitely. Whether you're a programmer, data analyst, or just curious, learning about graphs gives you a new way to see the world.
That's a great point. Okay, I think it's time to wrap up our deep dive into the world of graphs. It's been a journey.
It has.
But we want to hear from you, the listener. What are some cool applications of graphs that you've come across? Leave us a comment on our website. And until next time, keep exploring, keep connecting those dots, and stay curious. Bye for now. All right, welcome back for the last part of our deep dive, all about graph algorithms. We've talked about everything from what a graph even is to some pretty amazing applications like, alien languages, figuring out how social networks work, all that. So now let's bring it home. Why should any of this matter to you, the listener? How can knowing about graphs actually make a difference in your life?
That's the big question, right? See, the thing about graph algorithms is they're not just like some theory stuck in a textbook. They're tools, real tools for solving problems. And they're already having a huge impact like all over the place.
Okay, I'm listening. Give me some examples. How are these algorithms actually making things better or faster or just more, interesting?
Let's start with, GPS. I bet you use that all the time. Yeah.
Pretty much daily, yeah.
So when you're asking your phone for directions, it's not just showing you a map. It's running a graph algorithm, finding the shortest or sometimes the fastest route. It's treating those roads as edges, intersections are nodes, taking into account traffic, road closures, all that stuff just to figure out the best way to get you where you gotta go.
Wow, so those little blue lines on my phone, that's some serious math happening behind the scenes. That's pretty cool. What else? What other everyday stuff uses graphs?
Think about those people you may know suggestions on, like social media or when you get recommended movies or music, products, all that. Graphs are behind that too.
Oh yeah, those are always kind of freaky how accurate they can be.
Right. They're analyzing the connections between people or between people and the stuff they like to figure out what you might want next.
So it's not just connecting people, TO people, it's people TO information to, experiences, things that matter to them. I'm seeing how knowing about this gives you an advantage, like navigating the digital world and all.
Yeah. And it's not just about convenience either. Graph algorithms are being used for some really big problems too, like healthcare analyzing medical data, finding patterns in diseases, even personalizing treatment plans,
Wow.
or finance detecting fraud, managing risk, making smart investments. Graphs are involved in all that.
So we've got graphs getting us around town, connecting us with people and info, maybe even, saving lives and protecting our money. It's kind of mind-blowing how much they're doing behind the scenes.
It is. And as our world gets more and more interconnected and as we create even more data, these graph algorithms, they're only going to get more important. They're how we're going to make sense of it all, connect the dots, find solutions to the challenges we're facing.
Okay, I'm sold. Graph theory is something everyone should know about, at least a little bit.
Mm-hmm.
But where do you even start if you want to learn more?
Don't let the fancy words scare you off. The basic ideas, they're actually pretty easy to understand. Start by thinking visually, like networks. Think about how things are related, whether it's people or places or ideas, whatever. Once you see the world through that graph lens, you'll be surprised how many places you find them.
So shift your perspective. See the connections that aren't always obvious. Any resources you would recommend for people who want to dive deeper?
There's tons of stuff, online courses, tutorials, even games that can teach you the basics. And the best part is you can start using what you learn right away, even with small projects. Build a graph of your social network or map out the characters in your favorite book. There's no limit to what you can do.
Great advice. Start small, have fun, and don't be afraid to experiment. So to all our listeners out there, keep exploring the world of graphs. You never know what hidden connections you'll find.
And who knows what problems you might solve. The power of graphs, it's just waiting to be unlocked.
Thanks for joining us on this deep dive into graph algorithms. We hope you've learned something new, and I don't know, maybe even gain a new appreciation for the power of connections. Until next time, keep those graphs in mind. You never know where they might lead you. See ya.